Here we are getting deep into what I call the heart of linear algebra, solving the system Ax equal to b. What we have learned is that by some row operations you can reduce n cross n matrix A to U, upper triangular matrix, and then by backward procedure, backward substitution as they call it, you can get the solution. Now the idea is that if you take a usual matrix and then trying to do a row operation may not be very intuitive, might feel a little bit problematic to do it. Even to compute it is not so easy. It's not pleasant, I would say sometimes. Is there any easier way of doing it? And this is where the power of matrix theory comes into being, and the beauty at the same time. Suppose I have a 3 by 3 matrix. So if I want to drop the number of the elements below the diagonal to 0, there are 3 elements. So as you have learned in the last class that there must be 3 row operations. So first I have to drop the element in the position A21 to 0, then A31 to 0, then A32 to 0. Okay. How do I do that? That's a curious question. So in order to do that, I will take a more simpler approach. The approach is this, that I would multiply A, the matrix, from the left with 3 matrices which we'll call elementary matrices, if I multiply them successively by 3 matrices, I'll get the matrix U, the upper triangular matrix. And it will also transform, because I'll multiply both sides, it will transform B to B tilde or B bar, whatever. You might say that, okay, you are not doing it for n cross n matrices really, for generally you are just doing for 2 into 2 and 3 into 3. But these are the things which is handleable and it can be shown. Otherwise, things has to be done on machine. Now, what are these matrices by which I apply on the left side of A, multiply on the left side of A? These matrices are called elementary matrices. Elementary matrices are obtained by tweaking the identity matrix. So suppose I want to replace in the actual matrix A the row R, row 2, by multiplying the row 1 by some number alpha and then adding it to row 2, and that would become the new row 2 of the matrix A. What I do is that I take the identity matrix and do the same operation on it. Identity matrix being a diagonal matrix with, except the diagonal all entries are 0 and every entry is 1, it's very simple to do it. Once you have done that, once you have done a row operation on an identity matrix, we call it an elementary matrix. Some people like Gilbert Strang call them elimination matrices because they eliminate some element and drop the value to 0. So what happens is that when you take that elementary matrix and left multiply that elementary matrix on A, then the resulting matrix, say E1A, if E1 is the first step, you have 3 elements, so the first elementary matrix is E1, say. So if the E1A gives me the matrix that would have come if I have applied the same row operation on A itself. So what happens, instead of doing the row operation on A, I do the row operation on the identity matrix. And that is very important, that I am doing the row operation on the identity matrix, right? So let's understand. So what we will have, so E1, then you multiply by E2 for the second taking of A31 to be 0, dropping the value of A31 to be 0, then you multiply by E3. So E1, E2, E3, so those 3 multiply and that gives you the U. So E1, E2, E3, their product, maybe later let me call it E. So E of A is equal to U. And these elementary matrices does have inverse matrices. These are n cross n matrices which are actually surjective mappings between Rn and Rn, and but the bijective mappings between Rn and Rn rather. And so what happens is that these individually have an inverse, and hence the product has an inverse. So A is E inverse of U. So this E inverse is called that L that you have seen here on the top, writing as A is equal to LU, that is the LU decomposition of a matrix. So every matrix can be written as L times U. Actually, if you write every matrix as L times U, then LUX is equal to B, then L inverse of, because L is also invertible, because it comes out of an inverse of a matrix. So L inverse of B is U of X. So if U is invertible, then U inverse L inverse of B is X. That's it. So ultimately when you do the LU decomposition, you have to think about the inverse of a matrix, which is the inverse operator. If you think of inverse here in terms as that it is a inverse of a linear operator A from Rn to Rn. But because every linear operator on finite dimensional space are given by matrices, that we say that okay, A inverse is the matrix. Because it is from Rn to Rn, we actually would write the linear map as the matrix. Yeah, and that would be clear. And we just think only in terms of the standard basis. So the term inverse of a matrix is important, and given the inverse of a matrix as an inverse of a bijective map, what is the matrix representation of A inverse? How do I compute it as a matrix? How do I show what is that matrix which represents A inverse? That will be one of the goals of this two-part lecture. But to do this decomposition A, to reduce the matrix A to an upper triangular matrix, an invertible matrix is being used. So the inverse finding is a key issue. So sorry. So let us just start with a very simple matrix and see how do we find an inverse. So so what does it mean by inverse? Suppose I take a diagonal matrix and I say alpha, beta, gamma non-zero. So these are the only non-zero numbers and every other entry is 0. So we ask ourselves, what is the inverse of D? So which means there must be some matrix B which is representing D inverse, such that B of D, which is again a mapping from Rn to Rn, or D of B, which is again a mapping from Rn to Rn, must be the identity mapping. Right? So if D operates an element on Rn, it should bring me to a unique element again in Rn, such that B of that element would give back the previous element, and so vice versa. In the DB, you can understand what we mean. So that both of them would be same as the identity mapping, that from Rn to Rn, that is a mapping which leaves every point fixed, doesn't change anything, maps every point to itself, and hence it is represented. Identity mapping is represented by the identity matrix, right? Whose all column entry or all diagonal entries are 1 and rest are 0. Now, if I want to find that B, let me do it by brute force, and let me do it for a 3x3 matrix example. If you look at the book of Gilbert Strang or other nice linear algebra books like Cheney and Kincaid and many others, you will see largely examples are with 2x2 and 3x3 matrix, because that is more easy to understand, easy to check the calculations, and to get once you do with 3x3 matrices, you get an enough feel for what the thing is and what can we really expect out of the things. So anyway, let's get going, right? So how do I get going? So let's take the matrix B to have the operator B basically has a matrix representation B. D inverse has a matrix representation B, and that B is given as I have written it in a very general form, B11, B12, B13, and just you can understand what are the entries here. And then I know that B of D must give me identity, or you could have done D of B must be given give me identity. So I now multiply. You know, I first have to take the first row of this and multiply with the, or you have to take the whole thing and multiply with the first column, this whole thing multiply with the second column, this whole matrix multiply with the third column. It's up to you. So if I take this, so that would give me the three different columns of, right? So if so what we do, we take this one into first row into this, and second row into this, and third row into this. Those are the first entry columns of the new matrix, the product matrix. That is same, and either you do whatever, you are basically multiplying this matrix with this, multiplying this matrix second with this second column, multiplying this matrix second with this third column. So when you do this, you would get B11 alpha and B21 alpha, other terms are 0, B31 alpha. Similarly for here, B12 beta, B22 beta, and B32 beta. And similarly for this, B13 gamma, B23 gamma, and B33 gamma. Now if two matrices are equal, then all their corresponding entries, so if two matrices of the form Aij and Bij, I and J both are from n to n, if these two are equal, then what happens is that, what do I mean by equality of two matrices? Which means Aij is equal to Bij. Ijth entry of A must equal the ijth entry of B. As simple as that. So B11 alpha must be 1. Let us see. B22 beta must be 1. B33 gamma must be 1. Giving me B11 as 1 by alpha, B22 as 1 by beta, B33 as 1 by gamma. So the diagonal elements of this matrix is known now. The B matrix, that's known. 1 by alpha, 1 by beta, 1 by gamma. So what about the rest? So B21, for example, B21 alpha is 0. Because alpha is not equal to 0, so B21 must be 0. B23 gamma is equal to 0. If gamma is not equal to 0, this must be B23 must be equal to 0, and the rest are all 0. If I is not equal to j, all the bij's are 0, and so B is equal to D inverse is actually given in this form. So it is 1 by alpha, 1 by beta, 1 by gamma. Those are the diagonal entries, and every other entry is 0. Okay. Now suppose I have a diagonal matrix, the same matrix, say D, but I now do a twist. I say, okay, alpha and beta are non-zero, but gamma is 0. If gamma is 0, what do you now expect? What would the thing be? So he said, okay, never mind, I have no problem in life, I'll just go ahead and do the thing. So let me say, now what would happen is, here if you look at it, here it should be not B32 gamma, but B32 beta equal to 0, not gamma here. Please make a check. B31 alpha equal to 0, B32 gamma equal to 0, and B33 gamma equal to 0. Sorry, B13 gamma equal to 0. So this should be B32 beta equal to 0, right? Now you see what happens. So these are the three situations, 1, 2, and 3, where I have gamma, and I equate now all of them Now, for example, B33 gamma is equal to 1 and gamma equal to 0, right? So, gamma is already known to be 0. So, basically what does it mean? Here I will have a 0 and I'll have a 1 here, right? So, it doesn't matter. So, these matrices cannot really be equal. So, I cannot say that this inverse really would exist. Or here you can say, okay, now suppose gamma equal to 0. So let me assign, if gamma equal to 0, then let me assign any value. It doesn't matter. If gamma equal to 0, let me assign any value to this this B13, B23 and say B33. But B33 gamma should be equal to 1. Here it would be a problem. You cannot assign here it will be a kind of a misnomer. It will be a contradiction because B33 into gamma and gamma is 0 is equal to 1. This cannot happen. So when you put gamma equal to 0, you cannot say that there is a matrix B for which this is equal to this into this is identity. So you cannot show. Suppose you make a test. Say let us assign some non-zero values to these points in B. Right? B is 1 by alpha, 1 by beta, and I say, okay, let me put some non-zero values 1, 1, 1. Let me see what happens. Then if you multiply with them, you just see that it doesn't matter whatever value you choose here for these entries. It will never give an identity. And anyway, from here it is already clear that it cannot, these sort of things cannot happen here in this particular case. So if gamma equal to 0, you cannot find an inverse, which means that the matrix is not invertible. So it's not a surjective and not an bijective map. So means it's neither surjective nor injective, because for a linear map from Rn to Rn, as you have learned earlier, bijective and surjective are injective and surjective are the same thing. Now what happened? Why you think that when I put gamma equal to 0, when I put gamma equal to 0, I will not be able to find. I will not be able to find an inverse. What is that issue? What is that big issue that had created the fuss? Okay, so that has to be really checked up. So the big issue is the rank. So observe what has happened. Suppose what happened. Let us just have a look. Just give me a second. So what has happened is the following. What has happened is, once I have put 0 here, the rank of this matrix D drops from 3 to 2. First, it was a full rank matrix because all the column vectors and hence all the row vectors, the square matrix, was linearly independent. Here it is not, because one of the column vectors is 0, 0, 0, right? So what it means that once I drop the rank from the full rank status, invertibility goes off. So here I make a bold statement. Obviously you can prove it, but I'm just to cheer you up, I write that I'm making a bold statement that if A is a n cross n diagonal matrix D, n cross n diagonal matrix D is invertible if rank D equal to n. Actually, this is true for any matrix. Once you have a full rank matrix, your invertibility is guaranteed. When it is not full rank, your invertibility is not guaranteed. And that's the key issue. Here you have seen it openly for a given matrix. You have seen it for a diagonal matrix. But for a non-diagonal matrix, normal matrix, non-diagonal matrix, about which we will learn in the second part of the lecture, you will see that this idea, if I replace it with this, I cut this diagonal and just leave, I say n cross n matrix D is invertible if and only if rank D is n. That will be true. So D is invertible, of course, if and only if all the diagonal elements are non-zero. That was what was the key issue. When we have transformed A to U and we have the new equation U of x equal to B tilde, the fact that we needed all the diagonal elements to be non-zero was that we were guaranteeing the invertibility of that matrix. That is the idea. Okay. Now let us speak about elementary matrices. So what are elementary matrices? We have already said that elementary matrices are obtained from the identity matrix by elementary row operations. The row operation that you want to operate on a matrix, normal matrix, just do the same operation on the identity matrix and multiply that new form of the identity matrix, that is the row transformed identity matrix, which we called an elementary matrix, multiply A with it from the left, and then that's it. You will get what you really wanted out of A by directly applying on A. Now let us take again a 3x3 example. We will not go beyond 3x3 examples because I do not again tell you not to get into complex calculations unnecessarily. So you again illustrate by using a 3x3 identity matrix. Let me just tell you. So everything just keep in mind. So there are three types of elementary matrices which we use. One of them is this. Say replacing a zero element with some number, non-zero entry. Say beta is some number, non-zero. Obviously, it's vacuously, even if you say this is also zero, replacing 0 by 0, it doesn't mean anything. It's obvious. I mean, you don't do anything. No. So now what we do, what is that operation? What we have done, we have multiplied the second row by beta of the identity matrix and then added it with the third row and replaced the third row with this, beta R2 plus R3. Now you multiply this on a given matrix. Then on finally the product of this matrix and the matrix say A here, that will result in a matrix that in which you have done the row operation on A itself. The new matrix is the row transformed A matrix. That is the key idea. Second type is replacing 1 on the diagonal by some other number. Negative, positive, doesn't matter. Right? So what you do? Basically you multiply R2 with alpha and replace R2 with that new vector. See, please understand, when you go back to the last chapter's discussion on forming these EX1, X2s and E2, X1, those kind of equation formats and showing that elementary transformations, these row transformations make sense because they don't change the solution of the equation. That's the key idea, because if they change the solution of the equation, then elementary row transformations would be absolutely useful. The power lies in that simple observation. That simple observation has all the power that is unleashed by Gaussian elimination, and that's what we are now looking at. So this is called a scaling operation, right? The third is a swap operation where you exchange the rows of I. The third row and second row have exchanged places, right? Here, or you can say third column and second column has also exchanged places because they look the same. It's a symmetric, nice matrix actually, the identity matrix. So I again read from what I have written, but I have been repeatedly telling you this thing so that it gets into your mind that the main idea of using elementary matrices is the following. If you want to carry out an elementary row operation on a matrix, then do the same operation on the identity matrix and create an elementary matrix and left multiply with A. Then the product would result into the matrix that one would obtain by doing the row operation on A itself. So the row operations are shifted over to the identity matrix, and that's the whole power. That doing it on a simple matrix, you can still do whatever you want. So let me take my favorite matrix. This, I don't know, it was told me the first day I learned determinant at St. Xavier's College, Calcutta. This was the matrix that was given and shown that the determinant was 0. We have not spoken about determinant, but that will come very soon. So let me consider one of my favorite matrices. A is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. First row 1, 2, 3, 4, 5, 6. Third row 7, 8, 9. Now suppose I want to replace the third row by 5R2 plus R3. You know what will happen if I multiply this here. 5 into R2 means 4 will become 20. Then this will become 25. And 6 will become 30. Now you add it with the row 3. So 20 plus 7, 27, 25 plus 8, 33, 30 plus 9, 39. So 27, 33 and 39, these would be the new entries of the transform matrix. So the transform matrix would be 1, 2, 3, 4, 5, 6, 27, 33, 39. Okay. So let us see what happens if I do the elementary or row operation. Do the elementary row operation on the identity matrix and then do 5 into R2 plus R3 and then replace R3 with that. So you will get 1, 0, 0. You multiply this with 5 and add it with R3. So you will get 0, 5, 0. So add it with R3, 0, 5 plus 0 is 5 here. 0 plus 1, 1 here, that is R3 is now replaced with this. Now let us multiply these two matrices. You see what you get here. So this will be 33, sorry, this is a mistake. This will be 33. Because here this will come like this. If you are multiplying here this with this. 0 into 2, 5 into 5, 25. 25, 1 into 8, 8. 25 plus 8, 33. So I have a mistake here. It's 33 here. There are printing mistakes and I am prone to that while writing. I'm pretty bad while doing some calculations with numbers. Abstractions delight me, but when it comes to real calculations, I am pretty horrible with that. I get stuck and look at myself. So that's about it. So you see the resulting matrix E1A is exactly the row transformation that we wanted to do on A. If I have done 5 R2 plus R3 and replaced R3 with that, the transform matrix of A would be this. Obviously here it would be 33 and that is exactly equal to E1A. So now you see the power of using elementary matrices. So you can try out other operations, that's what it is. I think I would not exceed the time. But first it is very important to know that you give me any elementary matrix, I can really find out its inverse, in the sense that, for example, if you take the first elementary matrices where you have multiplied the second row by beta and added to the third row and replace the third row with this. That is 1, 0, 0, 0, 1, 0, 0, beta 1. Now what happens? What is the inverse of this? Interestingly, the inverse turns out to be just replacing beta with minus beta. This will happen if I put any L here instead of 0. Then the same thing would happen. If I take the inverse, everything would remain same, L would be changed to minus L. Let us see why it happens. So our question is, what is the inverse of E1? And now let B be that inverse. And then say B is the one, we are taking the same symbols. B1, 1, 1, basically Bij, right? I runs from 1 to 3, J runs from 1 to 3. Now, this is, if I multiply this matrix, this is what I will get. Be careful, it is not like the diagonal matrix. It is not a diagonal matrix. Please understand. It is actually kind of lower triangular matrix here. It's not the diagonal matrix, so the things will be slightly different. So here would be the equations. So these would be 0, B11 would be 1, B21 is 0, B31 is 0. This would be 0, this would be B22 plus B23 beta would be 1. You see, I make so much errors in my calculation. So would be 1 and B23 is 0 and B31 is 0. This would be 0 and this B33 is 1. So what would happen here? How do I find all the inverses? B11 is 1 that you have stored up. B33 is 1 that you have stored up. Okay. Now, if B33 is 1, you get B32 to be 0. B33 is 1, B32 plus B33 is 1, so you'll get B32 is equal to minus beta. So B32, that is this place, should become minus beta, that is this place, should become minus beta. So I put this as minus beta. Right. Now, what is B22? Right. B23 is 0, so B22 is 1, right? So here I made a mistake. Now B22 is not 0, B22 is 1. So please correct these mistakes. B22 is not 0, B22 is 1, because you can see from here that B22 plus B23 into beta is actually equal to 1. I don't know how I make these horrendous mistakes, but then I write down the correct thing. Possibly because I know what it is. So this is a horrendous mistake. Do forgive me for this. This should be 1 here, and because you know that B23 is 0, so you can know that B22 is 1. And so that's it. And that is how you do the rest of the calculation, and this is your inverse. This is magical actually, that's it. Just change beta with minus beta, you get the whole thing. Now what we will do, that we will take a matrix on which we have done a row operation and reduced it to upper triangular matrix, and that we have done in the last lecture. Now we want to show that we would do the same thing by multiplying on the left with elementary matrices. That would be our aim here. Okay. Let us see. So here is the matrix. That it's from the same book on linear algebra and differential equation by Kapitula. That A is equal to 1, 0, minus 1, 3, 1, 0, 1, minus 1, minus 1. Our first elementary matrix, we'll mark it as A21, because if you want A to become an upper triangular matrix, you have to drop A21 position to 0. You have to eliminate 3 and drop it to 0. Get 3 out of the A21 position and drop it to 0. It might look very crude when I say this, but that is what you are aiming to do. You must have a 0 here in the transform matrix, because otherwise you're taking the first step to go to the what is it called, upper triangular matrix, and there will be three guys whom you have to throw out and get the 0, these threes, right? So I do the operation minus 3 times, as we have done earlier, minus 3 times R1 plus R2 and replace R2 with that. So we get E21 is this, and multiply E21 with the matrix that is given, and this is it. This is what we get when we apply the transformation, this directly on this matrix. You can check. When you apply directly, it is this. What we get is this. But if I do it this E21, this elementary matrices, it is just so simple. You have less chance of making a mistake. Even me would make less mistake. So if I apply the transformation directly on A, that is R2 is replaced by minus R3R1 plus R2, then I get E2 on A. The key idea is the following. The steps in row operations on A to get to U, right? That is identity to E21 is the following. The key steps is the following. On the identity matrix, when you apply Then replace row R2 by minus 3 R1 plus R2, you got E2 on. Then apply E2 on A to get E2 on A. The next step, we have to drop the position A31 to 0 in the matrix E2 on A. One has been made 0, the other has to be made 0 in the new transform matrix, because ultimately you have to keep on transforming. So our next elementary step is to construct the matrix A31. So what we will going to do, we can understand to actually, if I look at this matrix, which is the E2 on A, and if I know how do I drop this to 0, I have to multiply the first row with minus 1 and add it with the third row, and then I get a 0 here straight away, and I'll replace the third row with that. So what I'll do is E31 would be obtained like this. Apply on the identity matrix a minus 1 on the first row and add 1 on the third row, add it to the third row and replace the third row by minus R1 plus R3, and this is exactly what you will get, the E31, the elementary matrix. Multiply E31 from the left on the matrix E2 on A, and this is exactly what you get. So when you apply on E2 on A directly this operation, you will get E31 E2 on A. When you directly apply R3 is minus R1 plus R3, this is what you will get. The next step is to drop A32, and you understand, if I want to drop he make this 0, I just have to add R3 and R1. In this matrix, in this E31 E2 on A, if I have to drop the third one to 0, this is what I have to do. Just replace R3 with R2 plus R1. Now there is no role of there is no role of R1, because all the things below the row 1, the first except the first diagonal entry, all the columns below has been dropped to 0. So the job of row 1 is over. Now I am coming to the second diagonal element. All entries below the second diagonal element has to be 0. So now the role will come of row 2, right? So now what you have to do here, if you want to make this A32 to be 0, just add these 2 rows, that's all, and replace the third row with that. So if you apply on the identity matrix R2 plus R3, this is what you will get. And then multiply this A32 on A32, A31, A2 on A on this matrix, that is E31, E2 on A. Multiply E32 on E31, E2 on A. That is this matrix. And lo behold, you get your upper triangular matrix. Assume that the calculations are correct. And that's it. So what do I get? I get E32, E31, E2 on A. And I do not know whether I show you there, but if you take two matrices A and B, which both are invertible, and you want to take the, say, n cross n matrix, you take the product AB and you want to compute the inverse, then AB inverse is nothing but the product of B inverse into A inverse. This is very simple. Show that B inverse A inverse into AB is equal to identity. That's it. I leave it to you. So what does it mean? The product of these three matrices are also invertible, and A is equal to E32, E31, E21 inverse U. So this is your L. We can call this product totally as E. That is what I said at the beginning. So that gives you the decomposition A is equal to LU. Now let me calculate that L. L is nothing but, I can take this as, in the associative property of matrix multiplication, I can take this as A and this as B. So AB inverse, B inverse, A inverse, and again do the same thing on this. So you'll have E21 inverse, E31 inverse, E32 inverse. So 3-1 remains in the middle, and the last these two end positions exchange. So now L is this. So you know what is E21 inverse, you know what is E31 inverse, you know what is E32 inverse. You just replace it with minus. So here what was, let me go back, what was E31 2 1, I have to just replace it with minus 3, with the minus of minus 3, so it will become 3. E21 is, so E31 I have to replace it with just minus of this, which is 1, and E32 I have to replace it with minus 1. And that's exactly what we have. And when I multiply all of these, E21 inverse, E31 inverse, E32 inverse, I multiply, this is what I get, and that is your, that is, so what how do I multiply this? I multiply these two first, and then comes this, or left multiplication. So, and then this into this, and it will give you this, and then this into this will give me this. That's it. So that's your L. You have to check, multiply this with actual U that you have got, and see that the product is A. That check I leave it to you. So what would be the general rule for finding how, if you take a general matrix without numbers, can you write down kind of a schematic thing? Can you write down what should be, how do I know what is E21? Right? Directly. How do I know what is E21 directly, without thinking, looking at the matrix and say, okay, if I have to do this, I have to do minus of this and add with that and replace that. I don't have to do that. What would be the general scheme? This whole thing describes the general scheme, but that's too, it will be too boring to discuss in a class. We can discuss in our tutorial time, or rather our discussion hour. We can discuss this. We will not discuss this right away here, and this is too long. You will see how complex it becomes. You don't understand this complexity because this gets hidden, because you have just used numbers and everything gets shortened up, which is not true when you just keep the general form, and things can look very, very ugly. This minus this into these two products. So that's what I do not like. So what we will discuss, and then I write down a schematic algorithm for doing this LU decomposition, that is this transformation to the U matrix or Gaussian elimination. So I will discuss it, this scheme I will discuss in the other part in the Wednesday's discussion. And let me see if I can have some other discussion maybe, and I will talk about computing inverses in my next lecture. I'm leaving this part out of this direct lecture because I don't think this is too much to really keep on discussing. Anybody who listening to can't keep this concentration up with too many complications. So let's call it a good evening, and let me stop the talk where I did it with examples. I think that is enough to keep that in mind, that we had done the decomposition, LU decomposition of A. And hence, bye-bye and good night. Have a nice Sunday.